All right, welcome back to a second part of our two-dimensional kinematics practice problem where we are looking at R2-D2 being fired from the mouth of a swamp monster over level ground. And we are looking at part B here. We just figured out the range equation. We just learned why it looks the way it does and how to use it. And we used it to solve how far R2-D2 goes flying across the swamp before he lands on the ground. Now we're going to find out how much time does it take R2-D2 to make that journey from like that whole flight there until he hits the ground. And so how long is R2-D2 in the air? What is his hang time? What is his flight time? Now this one is actually pretty simple because there's something that's pretty cool that happens when you're working with two-dimensional projectiles. All right, when you're working with projectiles that happen, everything happens on a two-dimensional playing field here, X and Y. Then you can ignore one dimension. Like, in fact, actually, you need to ignore one dimension while you're working with the mathematics. Okay, because you really can't do both dimensions, like the motion of both dimensions mathematically at the same time in one equation. The range equation looks like you can, but really it's what it's doing is it's using that sign piece there to break apart a velocity that is actually two velocities. You know, this velocity where R2-D2 is being fired at an angle, it's really two velocities. It's an initial velocity forward and it's an initial velocity vertical. And we're going to use trigonometry to break that velocity apart most of the time so that you're working with just the forward velocity or just the upward velocity, but you can't try to use the initial velocity just as it is with the 22.5 meters per second unless you are working with the range equation or another equation that has already incorporated the trigonometry into it, and the trigonometry to break that initial velocity from into its components. All right, and that's what the sign is doing there. And for time's sake, to keep this video going quickly for you, I didn't show you how to create the range equation, but hopefully the explanation of why each piece is in there is sufficient. And it's very important, especially in physics, to understand the difference between direct relationship and inverse relationship. And just to review that, okay, what is directly influencing the range of our projectile R2-D2? Well, how far forward R2-D2 travels, the range, how fast R2-D2 was fired out of the monster's mouth, and the angle at which R2-D2 is fired. Both of those are directly related. If either of those go up to, if the velocity goes up higher, R2-D2 will go farther. And if the angle gets to the perfect angle, which we saw is 45 degrees, R2-D2 will go farther, okay? Now, the other thing, and that's what sine of 2 theta, like all that put together, gets the biggest value once theta is 45. And we saw that in our previous video. Now, the inverse relation, the variable, the thing that can vary, the variable that's inversely related to how far R2-D2 travels is the strength of gravity on this planet. If that gravity gets stronger, then R2-D2's range will get shorter. So with the inverse relationship, when one thing goes up, the other thing goes down. All right, and so when gravity gets stronger, we're dividing by a bigger number, as we looked at last video, and that is going to shorten the range for R2-D2. Alrighty then. Imagine that, gravity were 0. Well, then the range equation mathematically would break down. You can't divide by 0. And that would mean that there will be no range. That would mean that R2-D2 will never come back down. You just launched R2-D2 off the planet because this planet somehow doesn't have any gravitational pull. So as you just throw a baseball gently, and because of its inertia, an object will remain in motion. It will never come back down without that gravitational pull. Okay, enough of that. Let's look at how long R2-D2 is in the air. Now, this is actually a pretty straightforward deal, but I want to walk you through a very helpful process for solving two-dimensional kinematics puzzles. In fact, this is helpful for solving any kinematics puzzles or most puzzles in physics. So I'm actually going to use this. I'm going to create something I'm going to use throughout the entire rest of this series of puzzles. And this is going to be called a givens table. Now I'm going to create the givens table because I solve physics puzzles with a process called the guess method. So I'm going to elucidate the guess method for you now, and then we're going to use it herein. So the guess method is named guess, G-U-E-S-S, as an acronym. And an acronym, as you may know, is something where every letter in the word represents an entire other word, or sometimes an entire other sentence that begins with that letter. Now, the G in guess stands for givens. Okay, this is your given information. These are usually measurements that were taken for you and then given to you. If you're doing your own lab experiment, you often have to get your own givens by seeing what you can measure and then measuring it and starting with that to do what you can't measure, which is where math has to take over for you. And the U is the next thing you want, is what you want to know. So this is what you don't know. So this is your unknown. Now, a lot of times you're going to have more than one, so we might have unknowns, plural, okay? These are usually the things you're trying to find in a physics puzzle. And then there are connections, relationships between the givens and the unknowns, and those relationships must be established to see how the givens can reveal the unknowns to you. Those relationships we just call equations. Equations are literally mathematical sentences that show you how things relate to each other. And I showed you how in the range equation, it shows you how the initial velocity and the angle of the projectile are directly related to the range, and the strength of gravity on the planet is inversely related to the range. And that's all known and shown how they work by the equation there. By the way, I should say for those math minds out there, that the initial velocity is not perfectly directly related. What I mean is, like, we see that squared, it's actually got an exponential relationship there. So it's exponentially related in that as the initial velocity increases, the range will increase exponentially. Okay, now but the idea is that one goes up, the other one is also going to go up. One goes down, the other one's also going to go down in value. And the last step of the guess method, the last two steps are kind of interchangeable depending on how you like to work your equations out. Really, what's left to do here is to work out your equations. And how are you going to work them out? Well, first thing you're going to need to do is take the letters in your equations and put in numbers for them. So you can do plussing and minusing and multiplying and dividing. And so we're going to need to substitutions. You're going to substitute your givens. Okay, so maybe I'll just say that here. So we're going to substitute givens into the equation, right? And then you're going to solve with your algebra skills for the unknown that you're looking for. Okay, so I love the guess method. It helps me have a good place to get started, and often that is the difficult part of a physics puzzle. It's really not the algebra for most of us. It is the how do I get started in any situation. I could have all these different situations thrown at me, and this is a great way to kind of get your feet on the ground and get your bearings and then get something going. A lot of times we get frozen up and we get a little afraid and start panicking when we don't know how to start, and this is going to get you a way to start so that you can avoid that initial panic of not knowing what to do. Now, here's how we're going to walk through this process. The first thing we're going to do is we are going to list our givens. Now, here's how you list your givens in kinematics, okay? In kinematics, you really have to separate your variables to vertical and horizontal. And to do that, what I do is I create a givens table. I do this every single time. I highly recommend it. I've been doing this for, oh boy, I've been doing this over the decade and a half, and I still make these givens tables. So here's what my givens table is going to look like. First thing I'm going to do is I'm going to put a big old G in the top corner, because that's for my givens. Okay, that's my givens table. And then I'm going to put in an X and a Y for 2 columns. So we're separating my horizontal dimension and my vertical dimension, and I'm labeling them X and Y. And then I'm going to list the 5 different things that we could be measuring, okay, for the motion of these objects. We could be measuring, well, actually it's, yeah, I say 5, but we're going to see it kind of chunks out to a little bit more. So we're going to measure position, right? Position. Now, some folks are going to use an S for position, the letter S, as in super, something, you know, the letter S for position. That's fine. You can do that. I'm going to use an X or a Y, depending on which realm I'm in, which dimension I'm in. I'm just going to put an X down here so that I can kind of like, you know, now, sometimes it's helpful to know your initial position and your final position. So a little X naught for my initial, a little XF for my final, and some folks are just going to write an X for their final position. They're not going to put a subscript. I like to put subscripts because I like subscripts. And then what else can we have here? Let's go ahead and see how fast we're moving, right? So we're going to have our lowercase v, our initial velocity, and then our velocity at some point later, which I can put v, or I can put a little f there. And then we're also going to have, well, if that velocity is going to change, then we call that acceleration. So any changes in those velocities, we're going to track. And usually, well, and also I should say, why am I not putting an initial velocity, initial acceleration, and a final acceleration? Because this is kinematics, friends. And kinematics, the word literally means constant acceleration. So there's going to be one value for acceleration. Now that value is going to be different in the X realm and in the Y realm. It's going to be different, but it's going to be constant in both of those realms. Whatever it is going to be the same there. And then we're going to look at this happening over time, right? So now I'm going to put a delta t here because time is always changing. And I'm doing a lowercase t, and my lowercase t, I want it to look different than a plus. I don't want it to look like a plus, right? So I do a little swoopy on it to make it like a soft lowercase t. Okay? That's why I do that. So it doesn't look like a plus in my math. And here we go. Now, the reason why I put time at the end is because time is the bridge between these two dimensions. Okay, these two dimensions, whatever's happening in these two dimensions, is quite literally happening at the same time. So the amount of time it takes R2-D2 to fly forward across the ground and hit the ground someplace forward and go up and back down to hit the ground is the amount of time, same amount of time, right? It wouldn't really even make sense mentally, logically, if you tried to think of it otherwise. So what I do to show that is I'm going to put a little dashed line here to make a little table here. And then I'm going to put an equal sign across that. Equal sign. I'm going to use a different color because I can. And colors are great. So that change in time will be equal for every projectile ever across those two dimensions. And that equal sign is also a reminder to myself that that is the bridge between these two dimensions. Now, there's another couple cool things that you should memorize as a good physics student or a good physicist, okay? You should memorize that some things are given to us because of where we find ourselves, our planet, if this is happening on Earth. And some things are given to us because of our universe, like the way that gravity works in our universe, the way that projectiles work, because of the way gravity works, okay? Because a projectile is defined as an object that is under one force and one force alone, and that force is the force of gravity. And it may have been launched forward, it may have just been dropped. If you drop something and it falls out of your hand to the ground, it is technically a projectile fired with a 0 initial velocity, 0 meters per second initial velocity. You can throw it straight up and let it fall straight down, and it's technically a projectile during that time. And now, when it's in your hand, it's not. Your hand provides a force to hold it up, a normal force. But when it's in the air, it doesn't have anything acting on it but the force of gravity. Now, because of that, and because the force of gravity acts only in one direction, towards the center of our planet, there will not be any acceleration happening to your projectile horizontally. So in the X column, we get a freebie. We get to write a 0, and we're going to use the meters per second squared units for acceleration so that we always like get those very comfortable with those units in our head. And we also get to know that this is happening on Dagobah right now, which the problem told us is going to have the same acceleration as of gravity as on Earth. So we're going to put in a downward, and in this case we chose negative for our downward direction of 10 meters per second squared. And I know it's actually 9.81 meters per second squared, but we have to concede a little bit here. I'm going to make my math a little bit easier. It's really the problem solving, the puzzle solving that I'm interested in. I'm not interested in the minutia of the most specific numbers possible. This is really kind of a thought experiment anyways. And so minus 10 is going to be just fine. And for those of us that are super, super specific about that 9.81, one thing I would like to remind you of is that the 9.81 meters per second squared is not the same value everywhere on our planet. Our planet's gravitational pull actually fluctuates, as you should know if you're very picky about that piece of trivia. Okay, now let's see. Can we find some other hidden givens? All right. There are some other hidden givens. Now, there's some things we can decide for ourselves. Here's one that I usually decide for myself. My initial position, I usually say is position 0. So that gives me some more numbers to put in my table. So my initial position, I'll say this is 0 meters, and I'll say this is also 0 meters, okay? And so what this is my initial Y position, and this is my initial X position of 0 meters. And yeah. So, and then down here, if we want to put in our numbers here, let's take a look at this here. Just gonna move this guy over a little bit, boop, and let's do the same for this one. And move it over a little bit. Boop. Okay. Now let's take a look at what we would call these, right? So this is my horizontal acceleration. So I put a little subscript X next to the A. This is my vertical, over here, this is my vertical acceleration, but we actually have a letter for that because, you know, it's from gravity. So we use a lowercase g. And so I can put that. Now that's for the acceleration of gravity on the surface of a planet. Okay, usually 0 meters sea level elevation. Okay. Now another thing I know already from part A is I know my final horizontal position. I know this because I just figured it out. According to the range, the R2-D2 is going to travel forward. R2-D2 is going to travel from here to here. All right, and XF, the final position, is going to be what, like it's 47.6 meters away. I'm gonna get rid of this like little extra bit here. This is like if you were taking this as a quiz. You don't need that. We just want to solve the puzzle. So this is gonna be 47. Oh my! I've still got the big old thing. This is gonna be 47.6 meters. And if you look at this as a number line, the ground is a number line, then we said that this position was 0 meters on our number line, and to the left is the positive direction on our number line right now. That's what we decided in the first part, because that's the way that R2-D2 is traveling. So this is going to be positive 47.6 meters away from our starting point. So our final position is 47.6 meters. Long explanation for something that's pretty simple once you recognize it, but I don't want to jump to conclusions and I don't want to pass anybody by. So final position equals 47.6 meters. Now, for the vertical final position, you might think, oh, well, that's going to be 0 because R2-D is going to go up and he's going to come back down again. And he's going to land where he, at the same height he started, at the ground, over level ground. And you would be correct, but here's the deal, okay? This is true for projectiles. This is true for stories. If you want to tell a happy story, it depends on where you end the story, right? Now, if you want to be happy working with projectiles, and you want your math to be happy, it can depend on where you end the story, okay? So think about where you want to end the story, because sometimes you may actually want to work with R2-D2 at the tip top of his flight, okay? And if it's at the tip top of his flight, then your final vertical position is going to be the maximum height, maximum Y position. Sometimes you want to look at it like that, and we're going to see that later on. And sometimes you might want to look at it where it's the entire trip, okay? And at that point, you would want R2-D2 here back at 0 meters. The other thing you want to think about, though, is think about where you are in your story, okay? And I need to be consistent across my two dimensions. And what I mean by that is that if I am going to use the full trip here, that's the end of the trip, that's how far he is at the end of the trip, then I do need to use that full end of the trip there as well. All right, so it's something to be said about consistency. We need to make sure that we're being consistent. Okay, let's get rid of that. Let's get rid of that. So for now, because I did put, and what would you do if you wanted to use the maximum height here? Well, something that's really cool about projectiles is that let's see, this is the flight path of R2, right? There's the flight path. We're going to draw a parabola. Wow, parabola. Okay, and this path is the trajectory. Okay, every projectile gets a trajectory, even if it's just like you dropped it and it falls straight down. The trajectory is the path of the parabola. And I usually draw these, and most people usually draw these with dotted lines. It's not a solid thing. And because the shape of a projectile is always going to trace out a parabola, we call projectiles trajectories. We call this one a parabolic trajectory. And a parabolic trajectory is always going to be the shape for a two-dimensional projectile. Okay? It's always going to trace that out. Two-dimensional projectile. And we are ignoring air resistance in these puzzles, by the way. Now, that's the terms, okay? Now, here's what's pretty cool about this. This is a symmetrical shape, okay? And so that means that there's a cool bit of symmetry here. If we cut this down the middle, then here's where R2 started over here. Here's X sub naught, and that was position 0 meters. Boop, right there. And then here is X sub F, and that was 47.6 meters away. So right in the middle, like this middle spot here, that is going to be exactly 1/2 of the way. Okay, it's going to be exactly 1/2 of 47.6 meters. And on top of that, this spot at the top here, that, maybe I shouldn't even put an X, that is kind of a vertical spot, so maybe I'll put a little Y. That, my friends, there's a little Y. That is the maximum height. Obviously, you can kind of see that, right? The max Y position. And that occurs at exactly 1/2 of the range, which we see down here, 1/2 of the range. And it occurs at exactly 1/2 of the time. You see, it takes 1/2 of the total flight time, and we'll call that delta T, the change in time from R2 being launched to R2 being hitting the ground on the left. It's exactly half the time to go up, half the time to come back down. And that's really some cool stuff to keep in your mind. And the reason why, like, well, why? Well, R2-D2 is going to, he's gonna slow down as he moves upward. He's gonna slow down, till he doesn't stop moving. He's still moving forward at the same speed the whole time, but vertically he stops moving at maximum height. Okay, at vertical height, this is really cool. Your velocity y here for 1 instant, we call it instantaneous velocity, is 0 meters per second at that location. Okay, so at like Vy max, I'll put a tiny little max there. We'd say like your velocity at your vertical maximum position is 0 meters per second. And that is something that's huge sometimes for solving a projectile puzzle. Okay, so it's really nice to know, really nice to keep in your head. And why? Well, it literally has to stop moving upward so it can turn around and come back down, right? And then when it starts coming back down, I mean, it's not vertically, it's not moving very fast at first, and then it gets faster and faster and faster because gravity is constantly speeding it back up. And gravity, it's the same gravity that slowed it down while it went up as it is that's speeding it up while it comes down, right? It's the same pull of gravity, so it takes it the same amount of time to make the projectile stop as it goes up as it takes to bring the projectile back to the Earth as it comes down. Same amount of time. Okay, hopefully that makes sense to you, right? All right, so these are some cool things to keep in mind as we go forward in some future videos and we solve these puzzles. Now that I have this all set up, I've taught you the guess method. I've taught you the givens table for two-dimensional projectiles and how to put in the information you have right now. There's one other thing I want to show you here. Okay, and I'm going to show you how to get the velocity stuff. So here's how to get the velocity stuff. All right, let's see how to get the velocity stuff. Well, I told you that when an object is launched at an initial angle here to the horizontal, let's zoom in on this. Let's get real for a second. Put on your triangle hats, everybody. Trigonometry just means the study of triangles. So imagine a right triangle here. Remember, right means right angle. And then we're interested in the launch angle here. That's our angle theta. And I'm going to use that little rainbow symbol for the angle, right? And this is and so we need to break this apart into, there are two. This is our initial velocity vector, right? This arrow right there. I'm going to get rid of any extraneous arrows. So I was labeling that, but that's it, right? Now that is actually two velocities happening at once. That is an upward, that is an upward velocity, and that is a forward velocity, which I'm drawing right now. All right? It's an upward and a forward. I drew that a little too long. There we go. And you can look at it with the triangle I have right here. You can look at it like that. That's fine. Or you can look at it with a triangle like right here if you want to. And imagine the forward velocity right there. Okay? Whichever way you want to look at it. You know, it's totally up to you. And but what we want to do is we do want to look at it, and we want to use some trigonometry to decipher these two velocities. So we're going to have a forward velocity. We're going to call that v sub x. Okay. And then we're going to have an initial vertical velocity, and again, this is the same v sub x up here. Right? Whichever way you want to look at this. And we're going to have an initial vertical velocity, which we're going to see right here, or and that is v sub 0 y sub y. And the reason why I'm saying that is because that velocity right there, my friends, that's going to change. That's going to change, right? It's going to slow down as the object goes up to eventually become 0 at the tip top of the flight, and then turn around and be pointed downward, and then become bigger and bigger until it finally hits the ground. Okay? So that's changing. But why v sub x? Why did I not put a little 0 down here? Because it's not necessary. It's not. Because this velocity is not going to change. The horizontal velocity is not going to change. So this is going to be constant. But v sub y, v sub y, that's going to be constantly changing. Constantly changing. And we call that acceleration, right? Constantly accelerating. Constantly accelerating and how much? We know that it's going to be constantly accelerating by the value of g, which is negative 10 meters per second squared. Whoopee. Meters per second. Ooh, that's so ugly. Let's fix that. Meters per second squared. Yeah. So we do need to put an initial because that's going to be changing along the way, but we don't need to put an initial for the x because that is not going to be changing. That is going to be a constant value the whole time. There is no gravity pulling it forward or pulling it backwards in the direction of the ground, like horizontal parallel to the ground, right? Gravity acts straight down to the center of the planet. Okay, so there's that. Now, let's do the trigonometry piece, all right? So we need to figure out what is the initial vertical velocity, the VOY, and what is the VX, okay? What is that stuff? And so we're going to look at it as a triangle, bap, 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 with a theta down here and a right angle there. And so we're really looking for, hopefully you remember your sine, cosine, tangent stuff, all right? So we have, a lot of people remember SO, CA, TOA to think about sine, cosine, tangent. And SO is sine, S-I-N, abbreviated S-I-N. It's actually S-I-N-E. Sine of, or of means multiply. So sine of theta is equal to OH, all right? O over H, which O is opposite. Oh, wait, OPP for opposite. OPP, yeah, you know me. Over HYP for hypotenuse. 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 And that's the longest side of the triangle. That's the diagonal side of the triangle, right? And that's a U, by the way. I don't want you thinking that's an O. Whoop, hypotenuse. Now, what is the opposite side of the triangle? That's the side that's opposite to our theta. Like, our theta's looking out over here, and it's saying, oh, you're opposite to me. This side is opposite for me. So this is our opposite side, OPP on that side. And then we have one last side to identify, and that's the adjacent side, ADJ, ACENT. And we'll abbreviate that with an ADJ. And we're going to get even more abbreviated. Like, we can just abbreviate it down to that A, and opposite can be abbreviated down to the O. And now you can see where your SO, CA, TOA are coming from if we abbreviate hypotenuse with just an H. Ha ha! So let's kind of like da-da-da-da-da-da, da-da-da-da, da-da-da-da-da-da, da-da-da-da-da, ta-da. And then let's get an H here. Whoop, ta-da. And then we don't really need the dots. Beep, boop, pop, boop. Hooray. And get rid of that little triangle. All right. And let's get rid of this little like sight line of our little theta. Beep, boop. Wabba. Alrighty then. And right there. Okay, cute. All right, so SOHCAHTOA, right? So sine is going to give us a relationship between the hypotenuse and the opposite side of our triangle. Cosine is CA, C-O-S, abbreviated C-O-S, spelled C-O-S-I-N-E for cosine, if you want to spell the whole thing out. Cosine is going to be adjacent, ADJ, adjacent over hypotenuse, HYP. And then tangent, you guessed it, abbreviated TAN, so tan, spends all its time in the sun. Tangent is going to give us that. There's one combination we haven't seen yet, okay? We've got the opposite on the hypotenuse, and we've got the adjacent on the hypotenuse. And then we need we need something without hypotenuse in it. We need opposite and adjacent. TOA. All right, now all of that trigonometry review just so that I could have a little fun with you where we are going to now use these, okay? Let's use them with our velocities. Yay! All right, VOY is actually going to be the opposite side of the triangle. Let's see that. VOY. So that's the opposite side. And VO, let's put it in the, like here's its little hypotenuse spot, right? And let's go ahead and get rid of this. Let's just look at one of these two triangles. Let's look at the one that's drawn the same way I drew that SOHCAHTOA business. Okay, there we go. Nice and pretty, right? So now they look kind of the same. And so VOY is our opposite side. VO is our hypotenuse. And then so here's our hypotenuse. Here's our opposite side. Here's our theta. Here's our adjacent side. Okay, so we have that in our head. And then for we want to know VOY. All right, so VOY is going to be, it's going to be related to VO. We know VO is 22.5. We know the theta is 35 degrees. So we know VO and theta. So we need something that has VO, theta, and VOY. So we need something that has the hypotenuse, theta, and opposite. Sine is going to do that. Sine is going to have the hypotenuse, theta, and so sine of theta is going to equal the hypotenuse, which is VO, V sub O. And that's going to be over V sub OY. All right, so that is going to get me a relationship for V sub OY. And then I want to look at some other ones. What about Vx? Okay, so let's get Vx. So let's do cosine of theta is going to equal, and then it's going to be adjacent over hypotenuse. Oh, whoops, I drew my sign wrong. Whoa, hopefully you caught that. Yay. Okay, what did I do? I put the I flipped it. It's opposite over hypotenuse. Hutcheson. There we go. Oh, that's so much more beautiful. Love it, love it, love it. Okay, and then we're going to do adjacent over hypotenuse. Glad I caught that before I just shipped this video out and confused everybody. But ow, huzzah. Hooray, 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 hooray. That is going to get us our Vx and our Vy. Now, so you don't have to redo this all the time because this is quite a lengthy process. Look at this. It takes a while. How do you just memorize? Just memorize. Once you've seen this through, okay, and you know where it comes from, memorize this relationship. All right, now here's the way that you can really break it down. All right, let's go ahead and do some algebra in our heads. Okay. What can we do to solve this purple equation for V sub O sub Y? Multiply both sides by V sub O, and you're going to get V sub O sub Y on it by itself. All right. So you're going to get, and then I want to write, you can write equations, whatever's on the left can be written with whatever's on the right. You can switch them, right? You're totally allowed to do that in equations. Totally allowed to be like, I'm going to put this. Totally allowed. Make this pretty. Move it over a bit. La la la. Da da. La da. Oh, I'm getting the green too. La da da da. Totally allowed to do that, right? And then multiply both sides by V sub O. And what that's going to do is it's going to cancel out the V sub O on the left, and it's going to give you a sine theta times V sub O on the right. And so let's do that. Let's move our sine theta over and put our little V sub O here, so it's multiplied by sine sub theta. Ah, grab it. Grab it, friend. Yes, cute. There it is. And so that, my friends, is what you're going to memorize to use to find the V, the initial vertical velocity for a projectile launched at a angle above the horizontal. And we're going to do the same thing, exact same math, exact same process for the horizontal velocity as well. So we're going to let's go ahead and like assemble the whole thing over here. Haha. V sub x, and it's going to equal, and it's going to be multiply both sides of the equation by V sub O. So we'll have cosine of theta times V sub O. And I like to put V sub O in the front. So it's V sub O times cosine theta. And dun 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 dun. I drew that initial purple arrow because I was going to like redraw the whole thing down there underneath that arrow for VOY, but I never ended up doing it. So I just now I just deleted that arrow. I kind of had fun moving things around up here. All right, so this is our equation for the X and the Y velocities for a projectile launched at an angle. We call these the X component. This is the X component. Component means piece or part. So it's the X part or the X piece. It's the X component of the initial velocity. So it's the X component of the initial velocity. Okay, and then this was the Y component of the initial velocity. Y component. Why am I singing it? I don't know. La la la. Yoink. Memorize them. Memorize them. How do you memorize them? Glad you asked. So I don't know. I got a good one for when to do forces, but I don't have a good one for this one. You end up using them so much, you'll have them in your head after a while. All right, so now what am I going to do with these? What am I going to do? Oh boy, oh boy. We're going to take these and we're going to put them in our givens table. Okay, so V initial Y velocity. And that took a while, but you're really just going to write these like immediately every single time. Equals sine. Nope. Equals initial velocity times sine of theta. Okay. Now I'm not even going to write that, right? Because it's actually, we have numbers we can put in. That's going to be 22.5 meters per second from this problem or this puzzle. It's not really a problem, right? Times sine. We don't really have problems if we can't figure this out. It's an imaginary puzzle. Sine of 35 degrees. And then we have our Vx, which is going to be that initial velocity times cosine of theta, right? But we can put in numbers for that. We can substitute numbers in. So I'm going to go ahead and put in my 22.5 meters per second. Let's see if I can squish it in. Times cosine of 35 degrees. 35. Barely got it in there, right? Okay, and what you're going to need to start doing, like eventually, you're just going to have your calculator out, and as soon as you get initial velocity in an angle, you're just going to go ahead and crunch in, like multiply the initial velocity by cosine of that angle and write it down. Multiply the initial velocity by sine of that angle and write it down. Like you're just going to start doing that immediately in the future because you know you're going to need it. You know you're going to need it. All right, and then this final velocity for the x does not change. It's still Vx, right? It's constant velocity. So it's going to be that same stuff. It's going to be that same stuff from there. And the final velocity for the y, not VO, VF. That is going to be, now this is all symmetrical, right? So it's going to come back down and hit the ground, moving at the same speed that it was launched upward with. So if you do take this for the entire flight and you want to use it for that, it's actually going to end up being the same as the initial y velocity. It hits the ground at the same speed that it left the ground. If you ignore air resistance, which we always do in these initial velocity, these initial physics puzzles. So there we are, right? There we are. Now, let's take a look at, we don't know the time. We don't have that, right? We don't have that. So actually moving through the guess method, an unknown is definitely how much time it takes. And that is actually where we are with our puzzle. How much time is what they're asking for. So we're going to need equations that are going to connect these givens and this unknown. All right, so let's take a look at some of that. And we will do that in the next video. This video is long enough. See you there. Thanks for watching. You learned the guess method, you learned how to fill in a givens table, you learned how to find a bunch of hidden givens in a projectile puzzle problem, and you learned how to break apart an initial velocity at an angle into its component pieces. Hopefully that was helpful for you, and we'll see you in the next video to actually finish the guess method with this puzzle.